Okay. So I've never been to Nankai. Hopefully next time we will be able to go. Today, what I would like to talk about is about geometric singularities called symplectic singularities. This is after a definition by Arnaud Bourvil in early 90s. And I will report about recent progress that we had over a period of 8 years by now in understanding new aspects of those singularities. The main new tools that were developed are the Coulomb branch. We will explain briefly what they are. It provides a new construction for symplectic singularities and a tool to analyze those singularities, Hasse diagrams. Hasse diagrams have been used to analyze some symplectic singularities, in particular in the context of nilpotent orbits, and also slices in the affine Riemannian, but they are actually useful both as physical objects and as mathematical objects to understand the singularity structure of those singularities. I will be happy to accept questions during the talk. I could also wait for some questions. And I understand that there are also, there's time for questions at the end, so please feel free to cut me anytime. Okay, so the first point is that the singularities are of interest both in physics and in mathematics. In physics, in particular in supersymmetric gauge theories, in brane physics, in string theory, they show up as Higgs branches in various dimensions, up to 6. Can you see my mouse? Yeah.
Yep.
Okay. So they are also showing up in Coulomb branches of 3-dimensional equals 4 theories. In mathematics, they are also quite popular in certain circles of representation theory and algebraic geometry. They show up as closures of nilpotent orbits, which are quite intensively studied for several decades now. And in a more recent object as slices in the affine Riemannian. And these are just a few applications. I'm not saying all of them, but those are just examples of where they show both physics and mathematics. There are some different names that people are using. One of them is as hyperkiller cones or hyperkiller singularities. Sometimes people use the name holomorphic symplectic varieties. That's probably the most suitable names in which we as physicists are using it. And I think quite importantly, they are related to, you can find an analogy. So Goldstein singularities show up in Calabi-Yau manifolds, just like symplectic singularities show up in hyperkiller manifolds. Now, there are various ways to construct them. Here's a graph which shows a rough depiction. There is the set of all possible symplectic singularities. There are some ways of constructing them as hypercell quotients, and Andrew Dancer will talk in the soon, and he will probably use this or review about this construction. There is also one can construct, so just to say, hypercell quotients are used in physics for quite some time, at least since the early 80s. So they've been very instrumental in understanding many hyperkähler manifolds and hyperkähler singularities. On the other hand, Coulomb branches are more recent in understanding. They started showing up in mid-90s in the physics, and the big breakthrough in mathematics happened maybe 6-7 years ago. Now, so some of the singularities can be constructed using Coulomb branch, and actually that's where many interesting new spaces show up, where we couldn't study them before using hyperkähler quotients, and they produce very interesting physics, and also many attention. It attracted a lot of attention in mathematics. So there are some singularities which can be constructed using both methods. And then there's been quite some activity around what is called three-dimensional Beer symmetry. We should also say that there are Coulomb branches which are not symplectic singularities, just like hyperkähler quotients. And now the thing is that whenever there is a construction, we could study those singularities in great detail. That when there is no construction, there is unfortunately very few techniques. Maybe one of them would be the study of coadjoint orbits. So when we do have a construction, typically we would refer to a Quiver construction. So we will talk about it soon, but let me just say some words about the way we characterize symplectic singularities, and this list is ordered by ease of computation. So the simplest thing to do is to count the dimension of the singularity, and this can go as high as one wishes. One very important way to characterize is to specify the global symmetry of this singularity, and there is a lot of nice things one can say using representation theory. Next thing is the Hasse diagram, and we will touch it a little bit. It is characterizing the singularity structure of this singularity. Tells you how many symplectic leaves and the way they degenerate within this singularity. Next thing one can do, and now it really becomes quite heavy in computations. You could compute the representation content of the holomorphic functions, otherwise known as the Hilbert series. And for complicated spaces, this could be quite a task. If there is a high symmetry, then one can extract this information or recast this information in terms of highest weight generating function. And finally, one can do the hardest of all, specify the ring of holomorphic functions in terms of generators and relations. Now, how did we come about initially with Coulomb branches in physics? So typically it would start from some Lagrangian, maybe in the form of a quiver. And from this point of view, Coulomb branch is quite a complicated object because it receives many quantum corrections. But the advantage that we got in 2014 was that we managed to get all of those quantum corrections under control. And now we think of the Coulomb branches as the space of rest monopole operators. And the monopole formula has been quite instrumental in getting this understanding. So let me say a few words about it. It computes the Hilbert series for the Coulomb branch of a 3D gauge theory with 8 supercharges. So those are, it's a construction in physics. And actually that was the way we managed to get an understanding. And today there are some formulations which are purely mathematical of this 3D Coulomb branch. And so one doesn't have to refer to the original three-dimensional gauge theory construction. But in any case, once we had this monopole formula, it opened the way to evaluate the Coulomb branch on a very large set of moduli spaces and allowed us to understand moduli spaces in ways we couldn't do before. So this was really a big breakthrough in understanding. And I think very crucially, this monopole formula convinced mathematicians to study such constructions. And now we have a very nice way to prove theorems and to get new windows for understanding such singularities. Okay. Next, so one easy way of getting singularities is to start with quivers. And Nakajima quiver varieties have been around for many years, and they've been used to construct a collection of symplectic singularities using the hyperkiller quotient. But one should remember that given a quiver with which is some combinatorial data of some graph, there's nodes connected by edges with node labels. And then this allows me to not only construct the hyperkiller quotient, but also the Coulomb branch. So given a quiver, I really have two moduli spaces, not just one. And they are very different. They are related to each other through this thing which is called symplectic duality. It's quite an interesting relation. Perhaps Andrew Danso will talk about that. And then one important thing to understand is that given this quiver, both of those moduli spaces are symplectic singularities. So this gives me this richness in the construction. And I also wrote here a comment that we should not mistake, this is actually quite a common mistake to make, that we should not confuse symplectic singularity, symplectic duality with three-dimensional mirror symmetry. Those are two different phenomena, even though the way they were related to each other was kind of like a coincidence, which used 3D mirror symmetry, but you don't have to. So I put here a slide on the modular space of instantons. That's one of the nice applications of understanding symplectic singularities through the Coulomb branch. And the way it goes is that ADHM Quiver is a good construction of the modular space of instanton using hyperkähler quotients, but it only works for classical gauge groups. If you do want to understand the modular space for an exceptional gauge group, then you could instead use the Coulomb branch. And the Coulomb branch is defined for every gauge group, including the exceptionals. And here, as an example, I gave those two quivers for G2 and for F4. So once one computes the Coulomb branch for these spaces, and maybe I should mention that there's a work by Nakajima and Weeks, where they actually define those quivers in a mathematical way. And so this allows the study of such moduli spaces also from the mathematical perspective. Next, I'm moving to this previous point that I made, that given a quiver, one has two moduli spaces. Those ADE quivers are well known in the study of hyperkähler quotients. There's the work of Kornheimer and Nakajima, which show that the Higgs branch of those quivers are the Klein or Duval singularities. And then the point is that we can also understand these quivers if we compute the corresponding Coulomb branch. And if we do that, then what we get is the closure of the minimal nilpotent orbit of the corresponding algebra. And so here below, what we see is those guys are the Klein singularities. Those are the dimensions, 0 and 1. And here, what we are, this symbol says that this is the Hasse diagram. We will talk about this for the Higgs branch of those quivers. And then if I look at the Coulomb branch of those quivers, those lowercase letters denote the closure of the minimal nilpotent orbit of the corresponding algebra. And here there are the dimensions of those things. So X can vary depending on the dual Coxeter number of the corresponding algebra. So now we are led to discuss the Hasse diagram in more detail. Physically, it's a phase diagram, so it characterizes phases of the theory that is in discussion. In each phase, you have different set of master states. Mathematically, what we do is this Hasse diagram is made out of two objects, nodes and edges, and each node represents a symplectic leaf, whereas each edge describes a degeneration to a lower dimensional leaf. and the edge also is, as we saw before, the edge is also accompanied by a corresponding symplectic singularity, which tells me what kind of local degrees of freedom or local moduli I need to tune in order to move from one leaf, from a top leaf to a lower leaf. So this calls for a set of minimal degenerations. Minimal degenerations are those which have only two leaves, the origin and anything else. And this goes back at least to the work of Kraft and Pochesi, and even before Briscoe and Grothendieck. So following this work of Kraft and Pochesi, they classified the generations in closures of nilpotent orbits of classical type. And they just told us that those minimal degenerations or the minimal slices are either of type Klein singularity or of type minimal nilpotent orbit, which is precisely what we saw in the in those graphs here. So this we owe to the work of Kraft and Pochesi. They didn't do the exceptional case, but it was generalized. Actually, it took some time to generalize it to exceptional algebras in the work by Fu et al. And so, again, we get to the point that the minimal slice has a Hasse diagram with 2 points, as we saw in this example over here. And then what we can do using a quiver, if we have a construction using quiver, we can use the notion of quiver subtraction, and that is to take the construction as a Coulomb branch and start reducing the combinatorial data by subtracting the nodes that correspond to affine Dinkin diagrams. So here are the Hasse diagrams for nilpotent orbits of A type. And the reason I wanted to show this is that there is some nice symmetry where if I invert this diagram, this capital A becomes lowercase a, label stays the same, A3, A3, and so on. You could see that it has a nice symmetry. And this is because, or one of the reasons is that if I look at the quiver construction for the nilpotent cone, the quiver itself has a Coulomb branch which is equal to the Higgs branch. And so this calls for the notion of an inversion of a Hasse diagram. Given a quiver, we could just invert the diagram by taking the top slice and replacing it. So just invert the diagram and replace lowercase with uppercase. And so this thing is known as a Spaltenstein or Lustig, Barbara Vogan, several names related to this construction in nilpotent cones. But this can be also generalized beyond nilpotent cones to cases where we have either slices in the affine Riemannian, which Antoine Bourget will talk about in this meeting, or to cases where it is not neither nilpotent cones or slices in the affine Riemannian. So I will not have time to talk about the quiver subtraction. I believe we are past the time, so let's just over. So there is some algorithm for the quiver subtraction. It poses a conjecture for computing symplectic leaves for a given singularity. So that's a big challenge for mathematicians to prove or to just compute in our methods, and we could compare. And the most important thing is that it extends beyond nilpotent orbits. It reproduces what we know from nilpotent orbits and what we know for slices in the affine Riemannian, but one can do it for symplectic singularities which are not in this set, and then get a whole set of conjectures and their corresponding symplectic leaves. Okay, so let me summarize. The Coulomb branch is a new way of constructing symplectic singularities. When we use quivers, we should think of them as the analog of toric diagrams to toric singularities. They encode all of the geometric information which we need in order to understand symplectic singularities. The Hasse diagrams really give us very nice, valuable information about the singularity structure of each symplectic singularity in terms of leaves and slices. I didn't talk about brain systems, but really, when we look at the details, all of the progress that we got was essential. It was really a very important tool to use brain systems. For example, the quiver subtraction was derived from there. And finally, the monopole formula was the trigger which opened the window to all of the recent achievements. And I'm done. Thank you.
Thank you very much, Ami, for that lovely summary of a very exciting topic. And thank you for being so conscious of time. We still have 15 minutes, which is very ample for us to go and get some coffee or whatnot. Sorry?
15 minutes.
15 minutes, yeah. We have 45 minutes at your disposal. So I'll just, are there any questions of any nature from the audience? Just unmute yourself, whether it's technical or not.
Can I ask a question?
Yeah, of course, yeah.
Should we understand Quiver as a 3D n equals to 4 gauge theory, or it's just an diagram to specify the geometry?
So this is a very nice question. Thank you, Futoshi. It's good to see you.
Good to see
you. Indeed, the way we first saw this construction of symplectic singularities using the Coulomb branch of a 3D gauge theory, but now it has gone way beyond that. In particular, once the so-called BFN, the Braverman, Finkenberg, and Nakajima, used the way we think of it physically, and just thought about this construction as a mathematical one, and so I don't have to think about monopole operators. I don't have to explain what they are. I mean, I could, but many times the way we construct is not necessarily the way we use it. And I think that's a perfect example. I could just think of the data as the quiver data and from this to extract the holomorphic functions and the different leaves of the singularity without thinking of it as a Coulomb branch. And actually, this way of thinking about it was quite helpful. For example, in the work that we did together, Futoshi, on trying to construct Higgs branch in 5 dimensions, we just don't have to think of the Quiver data as a 3D Coulomb. It's just a collection of numbers, combinatorial data, which allows us to compute the properties of the corresponding moduli.
I see.
That's the nice thing about it. And so indeed, we started as a Coulomb, but it went well beyond.
I see. Thank you.
Any other questions from anyone? Yeah, there's a. So I'm actually checking the audience to see whether there are any members here who don't know what a quiver is, to keep in the spirit of complete dialogues. I think there might be, which is fine. Just let me know, and then we can have Professor Hanany just tell us even briefly what is a quiver gauge theory and why should we be interested in this problem. Yeah, I think indeed there are. So maybe yeah, I see some of my friends. There's an economist and a number theorist. So maybe Professor Hanany can tell them why is it that a theoretical physicist would. Now this is a very hard question, of course. So, but you'll forgive me. Why would someone be interested in doing a quiver gauge theory, or indeed what is a quiver and what is a gauge theory?
Okay, that's a good question. It sends us to the basics. So let's take a look at some simple quivers like here, or maybe even more complicated quivers like these guys, and possibly it becomes more involved in this set. And so the quivers show up in studies of physical systems already in the so-called standard model of particle physics, where one starts with the collection of force carriers that are given in terms of gauge groups, and so we call them in physics we call them photons, gluons, gauge bosons, and so that's in the heart of particle physics. Particle physics is based on a gauge principle, and one needs to specify the force carriers and then the matter fields, quarks, and leptons, and then it ends up with the very beautiful formulation of the so-called standard model. And there's a recent realization that the standard models is actually can be recast as a quiver, whether supersymmetric or not. And a quiver is just a coding of the data that is used. Instead of talking about quarks, gluons, photons, and so on, we just collect the data using some graphical information like what we see over here. And this encodes some of the interactions that those particles undergo. Now, there are many words to say about that. One of the points is to talk about supersymmetry and to compare the standard model, which is formulated in a non-supersymmetric way. There is a supersymmetric extension of that, but we need to have some experimental verification. And if you use a high amount of supersymmetry, which is more favorable to theory, then you end up with such quivers that we see over here. And it is not realistic as the standard model on the one hand, but on the other hand, it gives us very important tools to geometry and to various aspects of representation theory. And from this, we can extract a lot of physical lessons about the way particle physics behaves. Now, if we extend the study not just to learn about particle physics, instead we think about string theory, then the same objects of quivers show up in a very systematic way when we think about brains. And this has been actually the topic of PhD thesis of many of the people in the audience, to mention Yang Hui, when he started his first steps in physics. He looked at a class of quivers which arise on brains or in the vicinity of particular Goldstein singularities. And this led to a very beautiful dialogue between particle physics, brains on the physics side, and geometry, algebraic geometry, representation theory on the mathematical side. So there's plenty of things to say about the way, but quivers became kind of a tool. Not only it characterizes the data of the singularity, but it also gives us information about some theoretical world where I have gauge bosons and matter fields which interact in a very particular way, which is encoded in those graphs, those quivers. So I'll settle for this at the moment, unless there are more detailed questions.
Thank you very much, Ami, for that nice overview, which I'm already getting chats from some members of the audience who are not mathematical physicists thanking you for this explanation.